Okay, good evening, everybody, and welcome to this evening's HERMANUS astronomy presentation by Professor Du Toit Strauss, if I've got it right. So I'm just going to ask Peter Kotze to introduce him, and then we can get going.
Yeah, thanks, Derek. Good evening, everybody. It's a great pleasure for me to welcome Professor Strauss at our monthly meeting. I've known him for many years since my attachment where I was still working at SANSA. Du Toit is currently regarded as one of the leading figures in South Africa and also internationally with respect to the modeling and the observation of cosmic rays and the propagation of these energetic particles through astrophysical plasmas. So tonight he's going to talk more down to earth and tell us how cosmic ray particles are going to influence space travel. So Du Toit, it's a real pleasure to welcome you, and please, the floor is yours.
Thank you very much, Peter, and thank you for the invitation. Yes, I think I met Peter the first time when I was still a fourth-year student, I believe, which is almost 20 years ago, I think. Yeah, I miss going to HERMANUS. I haven't been there since the COVID epidemic, so hopefully at some point I would be able to visit again and yeah, maybe talk to you in person. Yeah, and thank you for the kind words, Peter. I'm not sure how much of it is true, but I appreciate the sweet little voice. So for tonight, I decided to talk about the work we do at the Northwest University, especially the group in Potchefstroom. And this is the work that the group here has been doing for probably 50 years, if not longer. And some of the older colleagues that are now retired and passed away are really, I would say, the international experts on the field of cosmic rays and their implications. So what I want to do is basically just introduce cosmic rays to you. I'm going to show some technical research we do in just 1 or 2 slides. So hopefully I don't bore you too much with that. And there's some take-home points at the end. So hopefully it's not very technical, and I hope you enjoy it. And so the cosmic rays and space travel part I've added because I've been watching Star Trek Picard the last couple of weeks already, which is the Star Trek I grew up with. So it's actually pretty emotional to watch it. And you all know the story about Star Trek. You have the captain in the spaceship exploring new worlds. And of course, if you look at these old Star Trek movies, technologically, we are nowhere close to doing this. There's a lot of engineering problems that need to be solved, and a lot of problems that are probably unphysical and that we'll never be able to solve. Like, for instance, having some strange warp engine core. But I think interplanetary travel is becoming realistic, and I have some slides about that at the end. But there's one physics problem that they never discuss in these sci-fi stories, and that's actually cosmic rays and what they do. So that's what I would like to focus on now. So for those of you that are into science fiction and you've heard the word cosmic rays before, there are some comic strips that actually have cosmic rays in the origin story, and that's the Fantastic Four. For those of you that's seen the movie as well, if you watch the movie, they were radiated by cosmic rays, and this gave them their superpowers. So that's the same cosmic rays I want to talk about tonight. So what exactly are cosmic rays? So the best way I can describe cosmic rays is with essentially doing a small little experiment, and we've done this a couple of years ago in Potch, and I think that's the best way to show what happens. Now, before I mention cosmic rays and what they do, it's useful to just introduce how we measure them. And you've all seen movies, Chernobyl series, videos on the internet. You've seen people using this device on the right, a Geiger counter, or technically more correct, a Geiger-Müller counting tube. And broadly speaking, it's used to measure radiation. But not just radiation, it's sensitive to charged particles. So it measures all kinds of ionizing radiation, protons, electrons, high energy photons, gamma rays, whatever. So on the movies, you have a little sensor that detects the particles. It's connected to electronics, and the readout electronics make a little beep each time it measures a particle. But you can also take that data, write it down, and have an idea of how intense the radiation is where you are. Now we've done this experiment. We've taken a smaller version of that Geiger counter. We've added it into a little polystyrene box, which I should have circled over here. In that box, we have a small microcomputer that digitizes or saves the data, and there's some temperature and pressure sensors in this box as well. So we take that box, we connect it to a weather balloon. This is the standard weather balloons that they use in geography, or what the Weather Service uses. We fill it with helium, we attach a parachute to it, and I think in this case there was a cell phone inside that you use for tracking. You let the balloon go and you look at the data. And the data during this experiment is shown in the right-hand figure, the graphs. It's a function of time. So it started measuring when we launched the balloon, and it measured for about an hour and a half before we managed to catch the balloon again on a farmer's field not very far from the university. And there's some interesting stuff that was measured. So for instance, if you look at the temperature, so that's the temperature inside the polystyrene box. It was summer in Poch when we launched the balloon, so close to 50 degrees Celsius. As the balloon goes up into the atmosphere, it gets colder and colder and colder, of course, at some point -10 Celsius. If you get high enough, the balloon stops expanding, it will burst at some altitude, and then as it falls back to the ground, the temperature starts increasing again. And you see the same with the pressure. So the atmospheric pressure, as you go up in the atmosphere, the pressure decreases and decreases. At the maximum altitude where the balloon burst, you had the lowest pressure, and as it's falling down, you go back to normal ground pressure. So for this specific case, we use the pressure to estimate the altitude, how high up in the atmosphere did we go. And for this case, I think we were probably about 17 kilometers into the atmosphere before it actually burst. So we got actually pretty nice data. So that's all very nice and good. The most important part of the data is actually the data from the Geiger counter, and that's shown in the stop panel. It shows the counts, or how many counts the Geiger counter, or how many particles the Geiger counter counted per minute as a function of time. And if you're on the ground, the counting rate is pretty low. You get a couple of beeps a minute. But as the balloon goes up in the atmosphere, you can actually see the counting rate increasing a lot, probably 100 times more where it bursts. And then as it falls back to Earth, it decreases again. So if you go up into the atmosphere, in general, the atmosphere is radioactive, and the atmosphere is much more radioactive than the ground level. So where do these particles come from? So we know today where they actually come from, and there's two main sources that create these particles that we measure in the atmosphere. The one source is to the left. These are astrophysical systems. So for instance, something like all these fancy stuff you hear about, black holes, exploding supernova, pulsars, pulsar wind, all these kind of exotic stuff you hear about, they all create particles. And these particles travel through interplanetary space, through the interstellar space, and at some point, some of them might hit our atmosphere, and that's actually where we measure them with this Geiger counter. So that's the one source that's far away from us. This is several million light years. We can't do anything about it. The second source is much closer, and that's the sun. So for instance, the image on the right, that's a zoom in of a big solar flare that happened at the sun. So there at the limb or edge of the sun, you had a solar flare, and in this case, the solar flare actually became a much bigger explosion of plasma, and it formed a coronal mass ejection. And during these violent stuff happening on the sun's surface, the sun can also accelerate particles to very high energies. And we can actually measure these on Earth's surface, actually on ground level even, if these events are high enough. So these are the particles we're interested in. They are called cosmic rays in general. They used to be called specifically cosmic rays because we only knew about the source at the left when we started studying this 100 years ago. So the idea is cosmic rays are essentially particles from the cosmos that reach Earth. The solar energetic particles, or the solar cosmic rays, these are more recent. They were discovered in the 1930s, more or less. And that's actually the thing that we are focusing on our research most at the moment. So you have particles, they come from different sources. They somehow manage to reach Earth. When they reach Earth, they have to get through the Earth's magnetic field. If they manage to do this, they still have to get into the atmosphere, so they could collide with air particles. And that's where they cause the major part of radiation. So why do we study cosmic rays? And this is a difficult question to ask a physicist in general. There's two answers. The one answer is because it's interesting. So I think most of you have that feeling. If something is interesting to you, you want to know more and more. So it's like a little itch you want to scratch. We want to know about the basic physics. How are these particles created? Where do they come from? How do they propagate, or how do they move from wherever they were accelerated to Earth? And how do they interact with our atmosphere, magnetic field, etc.? So that's the physics question. But there's also a practical answer to this question. Why do we study these particles? I've already given the answer. It's because they are radioactive. And as soon as you have people or electronics living or moving through a radioactive medium, you have problems. We all hear the stories about radioactivity causing cancer in humans. That seems to be definitely true. So if you have cosmic ray particles, for instance, they can interact with the organs, especially brain, eyes, internal organs of the human, through various processes. The one is they hit and damage your DNA, causing mutations, and that can then lead to cancer, for example. The second problem is electronics, and all kinds of electronics, even electronics like your phone. If you have high energy cosmic rays hitting the semiconductors or the silicon inside your phone, it starts changing bits. So the computer talks in ones and zeros. If you have a very high energy particle, it hits the memory chip or the RAM chip. It can change a 1 to a 0 or a 0 to a 1. And that has a big implication for if you're running, for instance, a very important code. So for instance, if you have an airplane using the autopilot, which is a computer, and the autopilot knows that you're at a certain altitude. If there's a high energy cosmic ray, it hits the RAM, and it changes the altitude from 10 kilometers to 1 kilometer, then you have a problem, because then the autopilot doesn't know what's going on. So you have these kinds of errors. You also have errors where the particle has enough energy, it simply destroys the electronics in there. So for this reason, the aviation and the space industry, they use very special electronics for these essential parts. They call them radiation hardened electronics. And there's a lot of way in the software where you can keep track of these errors, so ones becoming zeros and zeros becoming ones, because they're very important. So for instance, during the Cold War, when the US and the Russians or Soviet Union wanted to send ballistic nuclear warheads to each other, they had to account for cosmic radiation. So most of these old 1970s technology, intercontinental ballistic missiles, for instance, had 2 computers on each missile, and the 2 computers had to do the same calculation, and they had to get the same answer before they actually do any instruction. So it's important. If you launch something, you want to know exactly where you land. So that's basically the idea. We care about these particles because they cause radiation, and radiation causes damage to humans and or also to electronics. So we went through this experiment again. We took exactly the same Geiger counter that we had on the balloon, and we took it with us on a flight to Addis Ababa, from Johannesburg to Addis Ababa. And we got very interesting data that kind of shows why this is important, even for instance, airline pilots. So again, it looks like the first figure. The blue dots, no, let's start with the red dots. The red dots show the data from Johannesburg to Addis Ababa. At the top, again, it's the count rate from the Geiger counter, so higher counts mean more radiation. In the bottom, we also plot the pressure measured inside the aircraft. So this is not the outside air pressure now, it's the inside air pressure, but it's actually pretty interesting. And those of you that's been on planes long enough actually will start seeing some actually interesting stuff. So the data starts off at time 0. We are at OR Tambo already in the plane, waiting for them to close the doors. The pressure is pretty constant. Then there's a little bump at some point where they close the doors, they pressurize the fuselage, they basically pressurize the plane. The plane taxis, it takes off, and even the air pressure inside the plane decreases as you go up into the atmosphere, and then it stays constant, and then every now and then there's a little jump up and down before we land. And these up and down jumps actually track the flight levels at what altitude the plane is. So a plane generally uses air pressure to decide on what flight altitude is. You can actually see these little jumps in the data. But the interesting part is always the cosmic rays. What do they do? Similar figure like the balloon. The cosmic radiation is pretty low. As the plane goes up into altitude, it increases. There's a maximum peak. And then as you fly from Johannesburg to Addis Ababa, you actually see it decreases a little bit. And then once you reach Addis Ababa, it actually drops back down to 0. The return flight looks the same. You start off with the cosmic ray intensity as at Addis Ababa. You go up at some flight level. It's a maximum again. But now as you fly to Johannesburg, you actually see the cosmic ray intensity increasing. And again, you see the maximum over Johannesburg just before you land at OR Tambo. And this is an interesting illustration of something that Peter has been studying for a big part of his life, and that's the influence of the Earth's geomagnetic field on the cosmic rays. So Addis Ababa It's special. That's why we have so many scientific instruments there. It is right at the magnetic equator of the planet. And at the magnetic equator, the Earth is most efficient in shielding us from the cosmic rays. So at the equator, cosmic rays really have a very difficult time entering the magnetic field and actually passing down into the atmosphere. So at the equator, so at Addis Ababa, we have slightly lower count rates. Johannesburg is a little bit closer to the poles. So at Johannesburg, you have slightly larger count rates. If you then would continue to, for instance, the South Pole, you fly all the way to the South Pole, there's almost, for cosmic rays at least, they see almost no magnetic field there. So if you're at the polar regions, you have the highest levels of radiation. And that's also why, for instance, SANSA has a lot of instruments at the SANAI, at the South African base in Antarctica, because for cosmic rays, for example, we generally see a lot of them and they vary a lot. So we also have a neutron monitor that we operate there alongside the SANSA people. So basically, what this shows is it's a complicated process. The cosmic rays, it depends on how much atmosphere you have above you. So generally, if you go up in the atmosphere, the radiation from cosmic rays get more. And if you move into a weaker magnetic field, you have more cosmic rays. So for instance, people that are frequent flyers, is this radiation enough so you should get worried? I suspect not. So if you fly international a couple of times a year, it's not a big problem. It's not dangerous levels of radiation. However, if you're a pilot and if you are flight personnel that fly every single day of your life, there's a certain limit to the amount of radiation you can experience to cosmic rays, and the aircraft or the airlines do monitor the radiation levels exposed that the pilots and flight crew are exposed to. In most of the world, not the case in South Africa, but in most of the world, aircraft or airline flight crew are defined as radiation workers. So they have to go through the normal radiation tests, the same as someone working, for instance, in Kuiberg. So they have to monitor what type of radiation they are exposed to, and they have to monitor for long-term effects. And interesting, if you actually calculate the radiation, an average pilot will be exposed to much more radiation than someone working, for instance, at Kuiberg throughout their lives. So it's actually a big difference between the radiation levels, ground level, and in the atmosphere. So if you imagine that radiation is already a problem for someone flying a plane, imagine the problem for someone living here in the International Space Station for long periods of time. The International Space Station is what we call in space. It's in the beginning parts of space. So it's above the most of the atmosphere. So it's almost in the pristine interplanetary medium. So there's just a little smidge of atmosphere still above it. But the International Space Station is still well within the Earth's geomagnetic field. So the geomagnetic field does stop some of the cosmic rays hitting the space station, but they don't have the shielding due to the atmosphere. So the astronauts are exposed to much higher levels of radiation. And the type of levels of radiation that they are exposed to are not publicly available. There's a lot of tests or estimates what they do, what they are exposed to. But these are levels of radiation that would not be allowed on Earth's surface. So they are really exposed to a lot of radiation, even just on the space station. So now you should imagine what happens if someone goes to the moon. So there's an astronaut, hopefully in the next couple of years, on the moon's surface. The moon, of course, doesn't have an atmosphere, so there's no shielding from the atmosphere or shielding of cosmic rays due to the atmosphere. And for most part, for 90% of the time, the moon is also not in Earth's geomagnetic field. So these people on the moon surface are really exposed to all the incoming radiation. So the worst case scenario we have in this case is we have someone in the moon. This guy over here, he's outside his base, so he actually has absolutely no protection against radiation. The sun decides to have a fit and release a very large coronal mass ejection. All these particles move from the sun to the moon. They take about, in the worst case, let's say 20 minutes to reach the moon, and this poor guy is going to be exposed to all of that radiation. That's one of the reasons we actually study how these particles are accelerated at the sun, but also how to mitigate it. So what type of modeling or forecast do you need to do in order to warn, for instance, an astronaut that this is going to happen? And you might ask, what's the chances of this happening? Well, the chances are pretty good, actually. So there's a very nice graph that we always show just to convince the audience that these type of things actually do happen. It's a very complicated graph with a lot of different data points plotted on top of each other. It's tough as a function of time. So you can see the time starts from the 1950s here up to the 1990s, almost the 1990s. And plotted on top of this is the solar cycles. So for those of you that came early, Peter was mentioning solar cycle 25, where we're currently in. This starts at solar cycle 19. So you can see the sunspots going up, the thick line going down again. Solar cycle 20, which was actually, by the way, very quiet solar cycle based on sunspots. Solar cycle 21, and then we go on like that. So solar cycle 20 was very quiet. It didn't have a lot of these very explosive solar energetic particle events, but there was one important, very high energy one right there in 1973 and a bit. And this is indicated by this vertical thin line. What's more interesting is the thick dashed lines over here. They are labeled A11 to A17. And as you can guess, these are the Apollo missions, so starting from Apollo 11 to the last Apollo mission, Apollo 17. And right in between Apollo 16 and Apollo 17, you had this very big solar energetic eruption, which was the largest event in this whole time span of more or less 30 years. And it happened during a very quiet solar cycle, and actually not even at the maximum. It happened while the solar cycle was decreasing to solar minimum level. So it was pretty unexpected. Nobody expected this. The good thing is it happened right in between two Apollo missions. So a lot of people are working on this problem and actually doing the math, the calculations to see what would have happened if this event took place during an Apollo mission. And some of the people, there's some disagreement exactly what would have happened, but the consensus is it would have been a mission-ending event. So they would probably have, well, they do have iodine tablets on board the Apollo missions. So the astronauts would have needed to take the iodine pills, turn back to Earth, get back as soon as possible, and essentially hope they don't die of radiation poisoning before reaching a hospital. So these stuff do happen, and they are extremely dangerous. So this part I'm going to go through very, very quickly. I don't want to bore you with the details. How do we contribute in Poch? Well, we have different projects. We look at the theory, how these particles are accelerated. We have a lot of models that try to simulate how they propagate from the sun to Earth, for example. And then at the end, I'll show quickly some measurements that we have as well to make sure that our models somehow tell the truth. So the theory part, it gets complicated really quickly. It's very difficult to simulate how these particles behave when they get accelerated from the sun until they reach Earth. Because they are charged particles, they start gyrating in the sun's magnetic field. And because the sun's magnetic field is turbulent, it starts gyrating in this weird squishy fashion that needs to be simulated. So that's where the theory starts. We start by trying to describe this motion of a particle in a turbulent magnetic field. We put this into an equation. The equation we use, there's a simple form at the top. It gets much more complicated than that very quickly. We need to derive these coefficients that go into the model that couple the particles to the turbulence. Then you have equation, then you have to solve your equation. And to solve an equation like this, you have to run it on a computer. So you have to design and develop an algorithm how to do this. And then finally, if you do all of this, you can actually start making nice simulation results. And so there's a couple of examples we have here. On the left is one of the simulations where we try to predict what the solar energetic particle distribution would be after an injection acceleration event. So the sun is in the middle, the Earth is at 1 AU, so probably around this either red or green dot. These weird spiral curves, that's the magnetic field originating from the sun moving into interplanetary space. And these red and blue regions are just regions of high and low cosmic ray intensity. So we can run simulations like this. You can also take your simulation and put spacecraft in there. So all of these squares are current NASA and ESA, so NASA and European Space Agency spacecraft that are able to measure cosmic ray particles, in this case solar energetic particles. They are MESSENGER, which is currently circling Mars. It's in Mars orbit. Parker Solar Probe, that's been in the news recently, which went very close to the sun. Solar Orbiter is the European mission. Bepi Colombo is a European mission that is going to Venus at some point. Stereo A is a ESA NASA mission as well. And then at Earth, there's always a couple of spacecraft to measure these particles. So we run the model, we get these curves that are the predictions of particles at different position, different spacecraft positions. And then if we have a real event, we compare what the model gives to what the observations say. So for instance, here's an example of some events that really did happen. These are very small events. In 2014, there were 4 events within 2 days. So we run a little model that produces a prediction, or at least our model estimation of what would have been measured. So these are these red curves at Earth, the first panel. The second panel shows the same intensity, what would have been measured by MAVEN while it was still on the way from Earth to Mars. And the blue is the data point. So we try to find the model that can actually fit or explain the measurements best. And then hopefully at some point we can use that model to actually predict, if you have an event like this, how would this propagate between Earth and Mars. Now, an interesting thing is a project we started just before COVID. So we only did a couple of measurements and then the project actually died down a little. So we should restart it at some point. We developed with our German colleagues this dosimeter, which is shown here in the case. which is basically a very fancy Geiger meter that can actually measure the energy of cosmic rays in the atmosphere as well. And we started measuring the actual real dose rate of cosmic rays at aviation altitude. So the actual energy of the radiation that the pilot would be exposed to. And we had a couple of tests. There's a nice example of one of the tests on a flight from Johannesburg to Germany, I think to Munich, and then back from, it does look like Düsseldorf, back to Johannesburg. And during those flights, we could actually measure the real radiation absorbed by photodiodes in that box. And we could compare it to some model estimates. And in this case, you can see the model is overestimating the radiation. So this is the flight to Germany. That's the flight back to South Africa. So you can actually get to the point where you can actually do a calculation and compare it with what the model says. So what about the future? So the interesting thing for us at the moment is the Americans are definitely going back to the moon. You would have seen it on all the space websites. The Artemis program is running. I think in mythology, Artemis was the sister of Apollo, if I'm not mistaken. But anyway, the Artemis program has funding. Americans are going to the moon in the next couple of years. And the idea is to build a probably permanent lunar habitat and permanently have people living on the moon, essentially. So last year, near the end of the year, this rocket I have on the left-hand side, the Space Launch System, that was successfully tested. That's the spacecraft that's going to take Americans to the moon. During this test flight, so the crew are just in that little capsule at the top. It was totally uncrewed, so there were no astronauts on board. This poor dummy guy on the right, the dummy was there. It's let me just move this. It was put there on purpose. It was equipped with a bunch of experiments. I wonder if you can actually see some of them. So there's a bunch of experiments, a bunch of sensors everywhere, some radio electronics at the back. It measured all kinds of radiation that the astronaut would be exposed to when they move through the Earth's atmosphere, and all kinds of other medical stuff. So they are taking radiation measurements seriously for the Artemis missions. The NASA, with some of the international partners, are also starting to build the next space station. So the next space station, they want it much further away from Earth, completely out of Earth's magnetic field. They want it to orbit the moon. So the idea is the next space station will be called the Lunar Gateway. And the idea is you have people flying from Earth to the Lunar Gateway, and from the Lunar Gateway going back to the lunar surface, and having permanent personnel all on board. So this is an old sketch. It's not an updated sketch. They changed the layout a little bit. The Russian module is not happening anymore, so the Americans and the Russians will stop contributing to the space station that's going to be decommissioned in the next couple of years. And then the Lunar Gateway is going to take over. So some of these launch components are going to be launched, I believe, next year. And already the propulsion system will be first, then it will be this little command module thing. And in that command module thing, they already have a lot of particle detectors that will be on board and actually measuring particle radiation. So that's still in space. So that's actually, in terms of space travel, pretty close to Earth. So we are only about 3 days away from Earth. That's about the same time that you fly from the west coast of the US back to South Africa from a conference. It's not that far. The question is, what happens if we actually start sending humans to Mars? And I think it's not far-fetched, the idea of sending people to Mars. The rockets exist. Reusable rockets exist. That's the whole idea of SpaceX, to show that you can have reusable rockets. So there is, at least at the moment, no engineering problem that keeps us from sending humans to Mars. Everything is feasible. You'll have to have a lot of money, of course. You'll have to have some very willing volunteers, but it's not impossible to do this at the moment. The big problem with a mission to Mars is it takes 9 months to get there. So if you launch in a Hohmann orbit, which is the cheapest way to get there, it will be about 9 months of flight time for the crew to get from Earth to Mars. I mean, this is also not unreasonable. This is what they did back in the old days when they were discovering new continents on ships. It's 9 months sounds long, but it's still doable. Then the astronauts have to get to Mars. They have to build a house and a home to live in. And then if they want to get back, they have to wait another couple of months for the best planetary alignment, get onto the rocket again, hope it works, get back to Earth another 9 months. So you're looking at a mission lasting about 3 years. And during all of that time, they will be completely exposed to all the radiation that's around in the inner interplanetary medium. And on top of that, you might have some stuff happening on the sun that's going to produce even more particles. So at the moment, this is, at least if you speak to the NASA spaceflight people, this is at the moment one of the biggest problems with sending a mission to Mars. How would you protect the astronauts against radiation? We don't have any way to do this at the moment. If they're on the spaceship from Earth to Mars, we'll have to do the same that we plan to do with the astronauts in the space station. If we know there's an event coming, they have to take shelter, and taking shelter in a space station means they have to go to the special part of the space station, or the thing that's going to Mars, where you have the most radiation protection. So that's usually close to the water tanks where they keep the water, and you have to hide there and essentially hope that it's not too bad. So it's essentially a storm shelter for solar storms. Then if you get to Mars, they'll probably have to dig a hole, and you have to live in a hole just to protect yourself from the radiation. So that's really a big problem that is at the moment not solved at all. So at some point we'll have to solve the problem if we really want to be a multi-planet species. So at some point, something like this, if you see these artist depictions of a moon base or base on Mars, and this would be valid for the moon as well, by the way. You see these nice pictures of the domes, and inside you have trees and buildings, you have people walking around on the surface. That's all well and dandy, but you still have to do something about the radiation. So probably people won't be living on the surface. They'll probably be living in caves down below, and it will have to be pretty deep down below because Mars has a very, very weak magnetic field, and probably you'll try to spend the least amount of time outside unless we get a very nice way to protect ourselves from radiation at the moment. So this is already my conclusion. I went a little bit over time already. I want to just leave you with, let's say, 2.5 takeaway points. So if you forget everything I said tonight, that's fine, except that cosmic rays or charged particles, they present a radiation risk to astronauts and technology in space. And we want to protect against their harmful effects. But there's no way to stop the radiation. It's not like like Kuiper, where you can shut it down if it starts leaking radiation. You have to live in a way with these natural levels of radiation. And the best thing we can do at the moment is try to develop early warning models that's supposed to warn astronauts of something happening, and then hope that they have time to take precautions and essentially hope that they will survive the storm. So it's still pretty dangerous to travel in space. So with that, I think I reached the end, and thank you for your attention.
Sorry, just trying to unmute my mic there. Thanks very much, Du Toit. That was very interesting. On the protection, I mean, on the Earth's surface, okay, we've got a couple of kilometers of air above us, but I presume that graph of yours showed that the densest air obviously gives you the better protection. It sort of decreases rapidly, almost exponentially, as you get less dense and go further up. It actually I suppose it's getting exponentially less dense. But then magnetic fields, how much protection does the magnetic field, Earth's magnetic field, give relative to atmosphere? Is it sort of minimal? I mean, what about the idea of maybe putting a magnetic field around a spacecraft? Is that impractical? Or...
Yeah, so the magnetic shielding is significant, I would say. So the highest energy particles, they still manage to get through. But the Earth's magnetic field does keep out most of the lowest energy particles. And these are probably not the particles we should be most afraid of. So the
higher energy ones, it doesn't help.
It doesn't help much. But it does protect us from most of them. At the equator, at least, I would say. The problem is a magnetic field is one way to deflect the particles, but to generate a magnetic field comparable to what you would get at the equator is just, I think at the moment, unless they get like some superconducting magnet experiment going, would probably be unfeasible. So you need something with a stronger magnetic field as you, well, at least I don't think a man-made magnetic field at the moment would be good enough. And there's an added problem with the, sorry, maybe Peter can actually help us with this.
I was just the strength of the Earth's magnetic field, is it so strong that it's so difficult, so impractical to duplicate?
It's not that much of a problem. It depends on the orientation of the magnetic field. We must remember that the poles, the magnetic field lines, are perpendicular to the surface of the Earth, and that is acting as a funnel for energetic particles from outer space. But at the equator, it's parallel to the surface of the Earth, and that creates the majority of the shielding, although the magnetic field at the equator is about half the strength of what we have at the pole. So it very much depends on the inclination of your magnetic field for protecting radiation or shielding of the radiation. So that is basically what you need to have on a, I would say, an interplanetary capsule. It's not field lines that are perpendicular to the surface of the craft. It must be parallel to the craft, and that will create a lot of shielding, or the best way of shielding it from a magnetic point of view. So you don't need a very strong magnetic field, but it depends on the inclination and the angle of the magnetic field. So that is what my pennyworth of comment is from this side. But I would like to ask the 2A1 question. That is, what was the geomagnetic field conditions when you made the recording of the flight from Johannesburg to Germany? Was it a quiet time, or was it during the disturbed time, or what would be the difference if you have a magnetic storm prevailing while doing these measurements? I presume it would be it would be vastly different. For instance, flying over the poles of the Earth, where you would get an extreme amount of radiation in comparison to flying, for instance, over the equator.
Yep. Yeah, so for this, if we run the models, the biggest difference you see, of course, is at the equator. So the regions where we are flying through, it's not much difference, but you do see it. So we were lucky, we did these flights in should have been start of 2019. So that was right at solar minimum. So it was very quiet, KP index 1, very, very quiet. But if you do run the model for different KP indices, it does, at least in this model that we use, it does account for the compression or distortion of the magnetic field due to geomagnetic activity. And even on the scale of these figures, you do see some changes in there. And generally, if you have the squishing of the magnetic field, I think generally you have higher radiation, I believe.
Okay, that makes sense.
Anybody else with questions?
Du Toit de Villiers, thank you very much. It was a very interesting talk. You were very modest about the technical aspects of your research. I think that the screen that you're showing right at the moment is remarkably good in the sense that it actually follows the trends. You said it's predicting values too high, but can't that just be adjusted down by decreasing the value of the parameters, your coupling constants? My view is that this is very good.
It's not horrible, I would say. And if you have a model that predicts something dangerous like radiation, it's always better if your model is over predicting it a little bit than under predicting it, I think, in general. So for these cases, I think there's still some work to be done. So for the model, so the one thing is the models don't actually account for the actual airplane. So the airplane does absorb a little bit of the radiation, especially if you still have the wings full of fuel. So there might be some experimental issue in here as well. And then the models, originally they were all developed for space flight or airlines flying over the polar region. So you have, for instance, the flights from Chicago to Heathrow that goes pretty close to the pole. So these models were never fine-tuned for the equatorial regions because people generally just thought that radiation is negligible. They suck a thumb, the thumb sucker value. Pilots in South Africa are exposed to so many radiation, and they never actually went through the trouble of either fine-tuning the models or measuring it. So I think the trend looks okay. The little bumps, most of them we can explain, but probably in the next couple of years we should be able to get even closer and actually get the line through the data points at some point. So it's just a matter of time, and then we'll know exactly what's the problem, the coupling coefficients or whatever.
Is the model homegrown, or is it an internationally developed model?
For this specific case, I believe this is an international model that was run in this case. But this is an open source model, so I think anyone can actually download it and fix it in some sense and make it better.
Fascinating.
Thank you.
Just another question to come back to the protection side. Are there no materials which have any protection, or are they also impractical, like that has to be lead, which is too heavy, or something like that?
Yeah, probably something like that. It's too heavy. The radiation protection, for instance, for the space station, they do account for the actual material around the space station. So they say, I think they say it's something like a 5 centimeter aluminium equivalent shielding that you always have around you due to the aluminium and the whatever. There's a problem with cosmic rays and the nuclear physics because they are so much energetic. So if you were standing on the moon and you have a very high energy cosmic ray hitting you, it would probably, well, it will definitely go straight through you, and it might interact with 1 or 2 cells. So it has a lot of energy, but it goes through your body so quickly, it's probably not going to cause a lot of damage. The problem with the cosmic rays now is if you now add 5 centimeters of aluminium between you and the particle hits the aluminium, it interacts with the aluminium atoms, and it creates a shower of low energy cosmic rays. So instead of being 1 high energy, you have maybe 1,000 low energy particles, and all of those particles can then be absorbed by your body. And it's actually, if you're in space, it's actually sometimes more dangerous to actually have a little bit of shielding than just having no shielding. So it's a very difficult calculation to make it, and the same problem with Mars. So they do calculations of, if you want to dig a hole in on Mars, how deep should you dig? And if you only have 30 centimeters of regolith or soil, the radiation actually increases a lot. So you actually have to get this level correct. So if you want to shield yourself, you have to be careful to not make it worse somehow. So it's a very difficult physics problem to solve, that one.
That's quite fascinating. I think I'll wait for somebody else to go to Mars before I buy my ticket. Yeah.
So
I think,
yeah,
one thing that they consider going to Mars is to use one of these volcanic, or some of these volcanic chambers that exist on the surface of Mars, and that it looks like caves that you can actually crawl into, and then it reduces the amount of digging that you have to do. You don't have to act like a mole. You can just utilize the volcanic chambers that already exist there, and then use that as a sort of a shielding.
Yeah, so it would be interesting to see what they are doing. So at least the Americans are, I mean, they are planning for the moon habitat, and they're already building some versions of this habitat where the astronauts will live in. And I think they haven't decided the actual position on the moon where they'll have the base, but the idea is there as well is, if you just manage to get into a crater, so at least having like some high hills around you from the crater, that should already help by shielding some of these particles. So they have all kinds of fancy ideas how to solve this problem.
Yeah, at the moment, I think they are aiming for the South Pole, because there's the possibility of water that exists there is much higher than, for instance, at the equator. And so it looks like even the Russians are now aiming for the South Pole to make use of the water that exists in some of these old ancient craters.
Sorry, I've got.
I assume that the cascade of lower energy rays being formed from high energy is fairly well experimentally determined. In other words, you can predict what would happen for different materials and different thicknesses. You are nodding your head vertically, so that answers the question. Thank you.
Yeah, so there's a lot of work in material science in getting an optimal material, because you want to keep it lighter as well. So you have to do the calculation. If you build a decent heavy-ish spaceship going to Mars, it takes 9 months. You should calculate how much radiation you're exposed to, and then you should also do the calculation if you make the thing as light as possible and you use the biggest rocket you can find, and you maybe do the trip in 4 months instead of 9, would it actually be better to be exposed to all of the radiation for a short amount of time, or shielding for a longer period of time. So that's the type of calculations they're making now. And I should just mention, we also have a younger colleague in Poch that is doing material science, and they are actually at the moment actually looking at this, what type of material would be best. And if I understand her correctly, they are looking at these graphite tubes and all these type of modern stuff that might actually be strong and also pretty good at absorbing some part of the cosmic rays.
So, Du Toit, I see there are two of the attendees that have got their hands up. I'm not sure who was first called. Can you ask your question, please?
Yeah, let's go to Peter. He was first there.
Okay, Peter Harvey.
Yeah, okay. I just wanted to ask, is there any significant difference between flying at, say, 35,000 feet and 25,000 feet as far as the radiation exposure is concerned? Or is that actually immaterial, considering our shield is basically our magnetic field around the Earth?
Yeah, so it does have a altitude dependence, and it is generally better to be lower. So at the moment, the best. So I think most of you will know that in HERMANUS you now have the SANSA Space Weather Center, where they actually give predictions of these space weather events. And practically the thing they do at the moment is, if you have a airline flying over the polar regions especially, if they give a warning of a big energetic particle event, at least the idea is they will order the airplane to decrease in altitude to compensate for the enhanced levels of radiation. So I think I should actually get the numbers, but it's definitely still the best practice, if something like this does happen, to decrease and actually get that extra bit of shielding from the atmosphere for whatever it's worth in that case. It would be much higher, the radiation would be more extreme if you have these very high altitude planes, like the military planes and stuff flying at 80,000 feet or whatever. But commercially, I think the idea is still, if you have this happening, is to essentially dive and see how much atmosphere you can get between you and the event.
Thanks, Peter. And Cor? Cor Rademacher, have you got a question?
Yes, thanks for the opportunity. Excellent presentation, Du Toit. I would really like to have a quick chat with you after the session, if possible. I sent you a direct message, also with my phone number. If you didn't get it, I can give it here. But yeah, we have an upcoming high altitude balloon launch in the very, very near future. So I would like to discuss something with you.
Yeah, so that's something. We had a PhD student here a couple of years ago, and he was in charge of this whole aviation thing. And he had a couple of these high altitude balloons where he went to some of the local schools and got, I think, like the primary schools. And he got the kids to help do the balloon launch, and then they all drive in the bus to some farm somewhere, and I think they get paid in candy who can spot the polystyrene the first. And then they did try to do something similar in HERMANUS, which at that time we told them it would be a bad idea, because you have to look, I mean, you know about high altitude balloons, you have to get the permission from the aviation authority, and then you have to check the wind currents and the direction of the wind. So the people in SANSA managed to lose 2 of our Geiger counters somewhere over the Atlantic Ocean. So we should definitely talk with the, and I should have a look to actually see if we have any Geiger counters left. But that would be great if you have any project like that, and we can just like attach a payload
Yes,
to it?
yeah, we have an upcoming one soon, and we've been doing it for 11 years. Well, this will be the 11th year that we're launching balloons, and we have reliable recovery and everything. So, yeah, please contact me. We can have a chat and see if there's anything that we can fly.
Okay, no, I will do so. Perfect.
I would really appreciate it.
All right. All quiet for the moment. Anybody else? We still got here. No. Okay, if there are no more questions. Chris, sorry, I see your hand up now.
Yeah, I'm just sort of wondering, when you consider the accumulation over a lifespan, what would be the difference in the amount of radiation received by a person at the altitude of Johannesburg, roughly 1,600 to 1,800 meters, versus one at sea level, say in Cape Town?
Chris lives in
That, no, I mean, at least in theory, you should live longer in Cape Town, I guess, which will make everyone happy.
Yay!
But I think there's a problem with these radioactive or dosimetric measurements like we do here. So if you reach very, very high levels, where you can call it radiation exposure, then you definitely get sick. I mean, then there's a direct link between very high levels of radiation and someone getting, for instance, radiation poisoning. But the long-term effects of low levels of radiation is very difficult to measure and quantify. So even the case of airline pilots, for instance, they've been trying to do this for many years to actually see if there's the effect on the life expectancy because you have this extra radiation. And so far, it's inconclusive. On these levels of radiation, where you are not exposed to dangerous levels, it's it's almost like a random process. So you have this radiation, but there's random chances they actually do something bad. So someone might just be unlucky and get a cancerous tumor very quickly, and someone might be lucky and actually get away with it. The same that you have smokers getting lung cancer or not. And so the role of the genetics and the chance and the radiation is so close to each other, it's very difficult to say, even for the aircraft people. So I think statistically, the difference between Johannesburg and Cape Town, due to radiation, negligible. Probably at the moment, there's more pollution in Johannesburg, and that's going to take more years away from your life than the actual cosmic rays radiating you, I think.
We're probably breathing mine dust that's got uranium in it anyway, so that's another factor.
It's exactly that. And they've been doing studies, for instance, for many years, where they looked at cancer rates in flight personnel. And if you look, for instance, and this is a generalization that's probably not true anymore, but back in the 80s and 90s, if you look at flight personnel, they fly to somewhere, they get to the hotel, they have a couple of drinks, they're lying in the sun next to the pool, and that lifestyle is actually more dangerous than the radiation. So the actual chance of getting skin cancer from being outside is probably more. So it's a very difficult thing to measure long term, and it's definitely not conclusive. So the general rule they have certain limits. You're not allowed to be exposed to more than this amount of radiation. Is there for a reason, because if you are exposed to less than that, there's probably it doesn't contribute to any long-term effects. Something like that.
Thank you.
Can I just comment a little bit on that? I think the radiation from outer space is almost negligible in comparison to the radiation that you get from the sources in the ground. For instance, radon-222 is a very poisonous gas that comes from dolomitic regions, and in the United States of America, all houses must get a certificate that says that it is radon-free, because particularly in winter, when people close the windows, this radon can build up inside houses, and that is a huge source of lung cancer. So I think that is more dangerous than, I would say, an energetic particle from outer space. So
on ground level, yeah, on ground level, definitely.
Yes, exactly, yeah.
I think in the Western Cape, that has actually been historically a problem in Paarl. Actually, now that you mentioned that one. Can I just ask also, have there been instances of serious illnesses attributable to radiation where these space astronauts have been, up in space for many months or something like that? And do they have dosimeters or something with them, or do they just also have a Geiger counter or something like that?
Yeah, so they do have this in the space station. There's a lot of active experiments measuring the radiation and the particles in different directions and in the different, let's call them buildings. And then they also do fly with these passive dosimeters that they analyze afterwards as well. So they are pretty well monitored. So I'm not aware of any acute radiation problems. I think medically the biggest problem you have is issues with eyesight. So I think the eyes are the most sensitive organ to radiation. So there have been studies of not people losing eyesight, but having eyesight issues while they're on the space station, probably due to a little bit extra radiation. But I think there's never been any severe radiation events, and the long term, it's still inconclusive. Partly because if you're an astronaut, you do dangerous stuff. So it's again this problem, if you drive a race car or if you go to space, what's the most dangerous part? So, but there's a lot of people studying it at the moment, especially with the moon idea coming up. So hopefully we'll have a better idea in the next couple of years, I hope.
All right. Okay. Thanks for a very interesting, fascinating talk. Thanks for all the attendees. If there are no more questions, can we wrap up? Anybody else? Or can we wrap up? All right. Thanks to all the attendees for attending and for some excellent questions from amongst the group. And thanks, Du Toit, for your presentation. I'll send you a link to the recording.
It's a pleasure. Thank you very much.
All right. There's definitely some stuff I want to go over again. Thanks very much.
Thank you very much.
Okay. Thanks very much.
Thank you very much. Good night, everyone.
Good night, everyone.
Good night. Good night. Good night all. Bye.